All right, so yesterday we talked about how to draw the Lewis structures, but we didn't get to drawing them. So today we're going to start with exercise 6. So if you are with me, you are on exercise 6. Okay? It says give the Lewis structures for each of the following. So to do this, you have to know what group numbers each one is in. How can I figure out how many valence electrons an atom has? By the group number, by what column it is in. Okay, so hydrogen is in group 1, so it has how many valence electrons? 1. Plus fluorine is in group 7 or 17, depending on what kind of periodic table you're looking at. So it has how many valence electrons? 7. 1 plus 7 is 8. I'm going to divide that by 2. 8 divided by 2 is 4. So that means in this drawing, I should have 4 pairs of electrons drawn. Okay, that's what that means. Does everybody see how I did that? Okay. So since there's only 2 molecules, am I concerned about who goes in the middle? No. Okay, you just have to draw them. So I draw a single bond first. Okay. Now, does hydrogen need any more electrons? No, it only wants how many? 2. Does it have those 2? Yes. Where do the extra electron pairs need to go? Around fluorine, because fluorine wants how many? 8. So I count them up. 1, 2, 3, 4 electron pairs. So did I draw this correctly? Yes. We see that? Everybody have this, because I'm going to erase it to make room for the next one. All right, B is nitrogen, N2. How many valence electrons does nitrogen have? 5. And since there's 2 of them, I have to multiply it by 2. 5 times 2 is 10. Divided by 2 is 5. So that means I should have 5 pairs of electrons in this drawing. Okay. So we start off by giving nitrogen to nitrogen a single bond. Then I'd go and give them their pairs to satisfy the octet rule, but then I see that there's a problem with that. Why is there a problem with this? Because I've got 1, 2, 3, 4, 5, 6, 7. Okay? So that means I have how many pairs too many? 2. So that means I'm going to take this single bond and I'm going to add 1, 2, and make it a triple bond, which means then I need to erase these outside electrons. Now, does each nitrogen have 8? Yes. Do I have a total of 5 pairs of electrons? Yes. So is this the correct drawing? Yes. Two, 4, 6, 8. 2, 4, 6, 8.
Oh, okay. I was counting total.
It's okay.
10. I was like.
All right, C, NH3. How many valence electrons does nitrogen have? 5. Plus how many does hydrogen have? 1. We've got to multiply that times 3 because there's 3 hydrogens. 5 plus 3 is 8. And 8 divided by 2 is 4. So who goes in the middle?
N always, because H always.
So then I show it bonded to 3 hydrogens. How many pairs have I drawn?
3.
3. So where's that lone pair have to go?
On the top.
On the nitrogen.
Wouldn't that
Is that 4 pair?
force thing where
It will. So if we were going to do the geometry of that, it would look more like this. That's tomorrow.
wait,
Which would be trigonal pyramidal. Yay. I love geometry too. This is going to be fun. I'm excited about tomorrow. No, molecular geometry.
Okay.
Not the subject geometry. That was my worst math subject by far. Whoa. All right, so D, E, and F. Now, be careful on F, because F has a positive there. So that means you have to do what? You have to remove an electron, so you have to subtract one. Subtract D, E, and F on your own. Okay? After somebody gets D, come up here and draw it. When you get E, come up here and draw it. When you get F, come up here and draw it. Try it on your own. You don't know if you can do it till you try it by yourself. Sure. The least electronegative goes in the middle, or unless you're dealing with something that has hydrogens on it, hydrogen always has to be at the end. It can never be in the middle. Volunteer to draw D on the board? This is positive, so it's tricky. You gotta remember to take away an electron. Excellent job. Volunteer to put E on the board. And I'm going to look at F with you. I hope you got it. All right, how many valence electrons does nitrogen have?
It's got
5. Plus how many does oxygen have?
It has 6.
6.
Just taking away.
Okay. And this positive means I've done what?
Taking one away.
Please excuse the FFA members. They were running late. If they were marked absent, please let the office know so I can fix their attendance. Please excuse the FFA members. They were running late. If they were marked absent, please let the office know so I can fix their attendance.
All right. So this positive means I've lost an electron, so I've got to subtract 1. Okay, to show that I've lost it. So 5 plus 6 is 11, minus 1 is 10. So I divide by 2, and this shows me that I need 5 pairs of electrons. Okay. So I put nitrogen in the middle. I show it bonded to oxygen, but then when I try to fill in to give them 8, what do I notice? It's too many. It's 1, 2, 3, 4, 5, 6, 7. So that means I've got 2 too many, which means I need to change this single bond into a triple bond. So when I change that to a triple bond, that means I need to take away some of these electrons on the outside. Now do I have 5? Yes. Okay. And then since this is positive, I need to put this in brackets and put a positive symbol on the outside. We see this? Yes? All right. Now, let's talk about how sometimes we're going to have structures that violate the octet rule. We talked about this yesterday. We said anything in the third period or greater on the periodic table can do what? They can fill up the d orbital, which means they can make more than, they can have more than 8 valence electrons. They can have more than 4 bonds. Now, they can only have a maximum of 6 bonds. Okay? So if you ever put more than 6 pairs of electrons around that central atom, then you know you've done something wrong. Okay? So they can have 4, 5, or 6. No more than that. So, let's look at this one. Phosphorus is how many valence electrons? 5. Plus how many does chlorine have? 7. And I have to multiply that times 5. 5 plus 35 is 40. And if I divide by that by 2, that is 20. Okay. So we put phosphorus in the middle. And then we're going to show a single bond to all of the chlorines. Now, have we already violated the octet rule? Yes. Okay. Because I've already put 5 bonds around phosphorus now instead of just 4, which means it has 10 valence electrons. Is phosphorus in the third period or greater? Yes. So do I know that's okay? Yes. What's my next step? There you go. Put my dots around my chlorine. So then I double check myself. 4, 8, 12, 16, 20.
Can you count that one?
Sure. So this is 1, 2, 3, 4. So there's 4, 8, 12, 16, 20. Now, exercise 8. Now, this isn't going to happen on the first one, but I want to clarify. Sometimes we won't just have exceptions to the octet rule because we have too many. Remember, there's also exceptions to the octet rule where they're okay with having less. Remember, hydrogen's okay with only having how many? 2, which means it's only going to form how many bonds? 1. Okay? Beryllium was okay with how many? You remember? 4 valence electrons, which means it only wants to form how many bonds? 2. And then boron was your other exception. It only wants how many valence electrons? 6. So that means it's only going to have how many bonds?
Aren't there like elements that want to give away their electrons more than they want to receive?
All right, so exercise 8. Write the Lewis structure for each molecule or ion. So A, how many valence electrons does chlorine have? 7. Plus, how many does fluorine have? 7. And I have to multiply that times 3. What's 7 plus 21?
48.
8. Divided by 2 gives me 14. Who goes in the middle? Chlorine. Besides the fact that there's only one of them, how do I know chlorine goes in the middle? There you go. It's not as electronegative as fluorine is. So then I'm going to show fluorine single bonded to it. Put my valence electrons around the fluorine like I'm supposed to. Then what do I notice? I've only got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that means I've got what? An extra 2 pair. Where do we put the extra 2 pair if I filled up all the outside ones? Put them on the central atom.
I thought it was okay to have less.
Nope, it's not okay to have less. You have to have the exact number
Oh, well, then what was that whole? This you can have less.
on these. Those are the only ones where it's okay to have less.
I think
Can
you're
I
just
ask
giving
why?
examples.
No.
Like why is it okay to have one?
Why is it okay to have less?
Like why do they?
Okay, hydrogen only has a 1s orbital, which means it can only fit 2 electrons. Okay, beryllium only has a 1s and a 2s orbital, which means it can only fit a maximum of 4. Boron has the 1s, the 2s, and the 2p, but so if I did its electron configuration though, it would be 1s, 2, 2s, 2, 2p, 1, right? Yeah, I did that right. So it really just wants to fill in these 2. Well, let me rephrase that. What happens is these 2 jump up, and then it just makes 1, 2, 3 bonds there. Does that make sense? These 2 electrons jump up, and then it makes 1, 2, 3 bonds. We're going to do hybridization. We're going to get there, I promise. And then all of that makes sense. We'll do that in the next packet of notes. All right, let's look at B. Xenon has how many valence electrons? 8. Plus oxygen has how many? 6. I multiply that times 3. 8 plus 18 is? 26. I divide that by 2 and I get 13. So I'm going to put xenon in the middle. Oxygen, oxygen, oxygen. So then I check myself and I say, well, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've got an extra pair. Where must they go? Doo-doo. You try C, D, and E. I'm feeling a quiz on this tomorrow.
Go ahead. Do it. Do it if you're fast.
Feeling it.
Go ahead, do it.
Tomorrow's what, Thursday?
Nope, I'm
Actually,
feeling
yeah,
it
no,
tomorrow.
they don't bring a
Because then it's fresh in my grades months. I need good grades. I want to be a good grade.
Fresh is would be after you teach it, but not today. Like
It's not, did you grade my test?
oh, we have that lab Thursday. Still the lab.
We're going to do anything.
We remember.
Actually, since they're going to be wrong, it's not going to be enough stuff that everybody can have their own individual kit.
One day we'll be gone to screwed up, I guess.
Right, any volunteers to put up C? C, that really.
I think I got it. Made you think?
Do we want me to do it?
Sure.
Wouldn't it be 8?
I volunteer for C then. Yay me. Yay Snelly. Snelly's got it. How many valence electrons does Rn have?
1, 2,
8.
3, 8.
Plus how many does chlorine have?
7.
7. Multiply that by 2. What's 8 plus 14? 22. Divide that by 2 and I get 11. I'm going to put Rn in the middle. Draw it to a 4 ring. I'm going to have to erase my other handiwork. Draw it to a 4 ring. Put my dots. Put my dots. So that's 1, 2, 3, 4, 5, 6, 7, 8. So that means I need to go 9, 10, 11.
Okay.
That's what I
Because I saw like it's got 5, so whatever. But I forgot.
5 is fine. It just can't have, it can even have how many? 6. It just can't go over 6.
How do you,
Okay.
how do you like, I never looked at when you count start counting, right?
Uh-huh.
How do you count by each dot? Or do-
By each pair. So I count this as 1, 2, 3, 4, 5, 6, 7, 8. So now I know I need 9, 10, 11.
Are we gonna get up to like 3 elements, or it's 3 there, or is it always gonna be 2?
It'll pretty much be like this.
Okay, this might be an unintelligent question, but
No.
how do you know when you do like a set of electrons instead of a double electron?
The only time I'm going to add like double or triple bonds would be when I've filled everything in and it's too much.
Okay.
So then I know I've got to be able to take some away, so I've got to do that with double and triple bonds. If I've done it and it's not enough, then I know those lone pairs all have to go around the central atom. That's not unintelligent, that's a good question.
Pretty unintelligent.
All right, any volunteers for D? Yay! Volunteer.
You did.
Volunteers are good things. I need you to make that a capital B.
Yeah.
Shh. Excellent. Now, why is that a violation of the octet rule?
Oh, yeah, it's,
Doesn't look.
It's only got 2 pairs on PB.
There you go, because I only did 2 bonds on beryllium, which means beryllium only has how many electrons there? 4. But is beryllium okay with that?
Yes.
Yes, so we can leave that drawing as it is. Huh?
It can have more, but not all the time.
Beryllium, you really won't see it with more than 2 bonds. All right. E? Snellick is doing that one too? Okay, all right.
Yeah, I was confused on this one.
Okay, Snellick volunteers for this one as well. All right, here we go. So E, how many valence electrons does I have? 7. Plus how many does chlorine have? 7. And I have to multiply that by 4 because there's 4 of them. And I see that this is negative, which means I have to add 1 because that means I've gained an electron. So 7 plus 28 plus 1 is 36. And if I divide 36 by 2, I get 18. There we go. So I'm going to put my I in the center. I'm going to show my chlorines bonded to it. I'm going to put my dots around my chlorine. So I see that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I need 18, so that means I'm going to put them on my iodine.
Hey, before we go to the next page, can we
Sure.
do that little NO positive?
Sure. And don't forget, because I just forgot, put brackets around this and put the negative symbol.
I didn't forget it.
You should have. You should have volunteered, Chip. All right, you want me to go back and do the NO positive one? Sure. I don't mind at all. All right. We're going to do the NO positive. So, how many valence electrons does nitrogen have? 5. Plus how many does oxygen have? 6. But because that's positive, that means I've lost an electron, so I've got to subtract 1. So 5 plus 6 is 11, minus 1 is 10. If I divide by 2, I get 5. So I know I
Five
need
electron pairs.
5 electron pairs. Okay. So if I do it the way we do it originally, and I just single bond it to the oxygen, but then I give them 8, I notice that I've got 1, 2, 3, 4, 5, 6, 7, right? Okay. But I can only have 5. Yes.
Okay.
So that means I've drawn 2 pairs too many. So that means I know I've got to add 2 more bonds. Okay. Well, when I do that, that means I've got to take away these outer ones because then they have too many.
Does it matter
Okay.
which outer ones
So-
to take away?
No, it doesn't. 1, 2, 3, 4, 5. And the reason why I had to take away those outside ones is I'll do this in a different color. What if we would have just left them and we added those bonds? So then I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So now I've created way, way, way too many. And on top of that, nitrogen now has 1, 2, 3, 4, 5, 6. Which is fine if we're intentionally violating the octet rule, but we can't. We only have to have 5. See what I'm saying?
Yeah, I just I don't know how you got like 6 like electrons. Like when you first drew it, before you made the 3 bonds, you had like little 3 different pairs of electrons, and then the middle one, like if there's 5 of them, then how does that? I don't know. How to do that.
What are you saying?
I
So
don't
now
know,
there's
like,
5 pairs. 1, 2, 3, 4,
yeah,
5.
She was before you changed them, like why you drew it that
Like,
way.
it has 5.
But she drew it that way just to show, so that you could like show how that's too many.
Because normally we start with just a single bond,
Okay, yeah.
right? And so then, but we say, well, each of them have to have 8, right?
Okay.
So then when I do that, I say, but that's too many. So that can't be right. How many is it too many by? There's 7. I'm only supposed to have 5, so I know I've got to change it. Yes, ma'am?
Would you send Chance down to the office and he'll be back?
Yes, ma'am?
Why would you like put a bond instead of just taking away like 2 of the other one, like 1 from nitrogen?
What do you mean?
Like taking away a
You
pair.
can't just take them away. You gotta replace them.
Yeah, I can't just, look.
We just,
Okay,
we
so
just
you-
borrow those real quick.
So you're saying, why didn't I just, no, you're fine. So you're saying, why didn't I just go,
We just-
okay, so this is 1, 2, 3, 4, 5, 6, 7. I've got too many, so why don't I just go boom, boom? Is
Yeah.
that what you're saying?
Yeah.
Okay, because now nitrogen only has 1, 2, 3 pairs, which means it only has 6 valence electrons. Oxygen only has 6 valence electrons. No. We can go over, but we definitely can't go under. Okay?
So, yeah.
And no matter what, I've got to end up with 5 pairs, period, when I draw it. Not only do I have to end up with 8 pairs, but each of them have to have 8 valence electrons attached to them somehow, some way.
Okay.
Okay?
I think I'm
They have to. That's just the way it is. Okay? And like I said, now if I get here and I've only drawn 3, then I know I'm going to violate the octet rule and I'm going to have to add extra there. But if I've drawn too many, that's when I know I've got to go back and manipulate and make some double or triple bonds. Does that make more sense? Ish?
Yeah.
Okay. No, don't apologize for making me go back. If you don't get it, I need to know. All right, resonance structures. I don't even want to know, I don't think so.
Oh, yeah, you do.
All right, resonance structures. Resonance structures, and I'm really honestly going to skim through this because sometimes your notes can make it more complicated than it is. So just hang on to me for a second. Resonance structures just means there's more than one possible way to draw it. Okay? For instance, ozone is O3. So if I draw out O3, okay, I would end up with a single bond between 2 of the oxygens and a double bond between the other 2 oxygens. Okay? Well, looking at that, who's to say that I couldn't put the double bond on this side and the single bond on this side?
Mayday, said I.
I could, right? Does it matter? No, it doesn't matter. So when it doesn't matter, we draw both of them. And so we do that by just drawing a little arrow, a double arrow between the 2 of them, and say it doesn't matter. We could do it this way, or we could draw it this way. Now, when I look at these drawings, I say, I got a problem with this. Okay? I do. I have a definite problem with this. And my problem with this is the fact that they're all oxygens, right? Which means they all have the same electronegativity, right? So realistically, in real life, am I going to get an area where I've got a double bond here and a single bond here? No. Okay? Because they're all the same, so they should all be sharing equally. So we would change that drawing, okay, is we would just do a single composite picture. So we do the oxygen up top, the other two oxygens bonded to it, so I've got 3 oxygens, and then we do a single line with a dashed line. Okay? That means that I know that this single oxygen here, okay, has a sigma bond and a pi bond in here somewhere. Okay, that's all those double with the dashed line means. It means somewhere there's a single and somewhere there's a double. It could be either place. There's no way for us to realistically be able to tell. Does that make sense? Yes. So that's how we would draw it. So same thing with carbonate. Okay, carbonate is CO3 2 negative. Now, the only problem I have with this is they should have put brackets around this and put a 2 negative symbol there. Because remember, if it's a negative or a positive ion, we got to put brackets and we've got to put charges. Oh, you would do all 3 of them. Okay. All right. So that's to say we could have a double bond here, or the double bond could be there, or the double bond could be there. Right? Do we realistically know where it is? No, we don't. So then we could show the carbon in the middle with the double with the dash, single dash, right? So then we say somewhere in here there's double bond, right? Realistically, we don't know which one, but we do know there's a double bond somewhere. Now, if you ask me which one you should do on the AP exam, I would just draw the 3 different resonance structures and call it a day.
What's the negative? Is that a negative 2/3? Was that what?
They're saying that we're going to do formal charge tomorrow. We'll start with class, but the formal charge on all 3 of these is negative 2/3, negative 2/3, negative 2/3. And if you add them all up together, that's how we get the charge of the carbonate ion being negative 2. All right, so describe the electron arrangement in the nitrite ion, NO2 negative, using the localized electron model. Localized electron model is just another way of saying draw the Lewis dot structure. Okay, can we do that? Yes, we've been doing it. So how many valence electrons are in nitrogen? 5. Plus how many are in oxygen? 6. I'm going to multiply that by 2. And then because it's negative, I'm going to do what? Add 1. So 5 plus 12 plus 1 is 18. If I divide that by 2, I get 9. So I know I should have 9 pairs of electrons when I draw this. So I've got nitrogen, I've got an oxygen, I've got an oxygen.
Wait, so the
Yes.
oxygen is more electronegative than oxygen? 'Cause isn't it?
No, nitrogen's less electronegative.
Oh,
All right, so then I say, all right, so if I was going to do this, I would have to fill in all of the stuffies. But now I see that nitrogen only has 2, so it would also have to have 2. And then I say, this is an issue. Issue number 1, if I count these up, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many did we say we have to have? 9. If I've got 1 too many, that means I need to create a what? A double bond somewhere. So this is when I should automatically be clued into this is going to be a resonance structure. Because could I add the double bond in either place? Yes. So I pick a side. I'm going to pick the left side first. And I say, all right, if I put a double bond there, then that's what it would look like, right? I agree. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I would have to put brackets.
Wait, you have to do all of them? I thought you could just do the dash.
Make it negative. You gotta do it. Okay. And then I would draw a double arrow and say I could have just as easily drawn it with the double bond here.
So when you add that double bond, the electron pair gets taken away from the nitrogen and the oxygen.
Yes.
Why can't you just do the dash? What was the point of showing this at?
Just to show you how they do it.
No, I don't care if I can use it.
You can use it as long as you know how to assign the formal charge to it. So we'll go over formal charge tomorrow, and if you feel comfortable with it, you can knock yourself out. I don't like formal charge, so I just draw the resonance
So
structures.
I had to put like, I don't know what this would be. What would this would be, like a negative 1/2, negative 1/2? But I'm sure it gets a lot harder.
Yeah. You can do it. I don't have a problem with it.
Okay, first, why would we put 2 electron pairs above the nitrogen instead of just one? 'Cause we had
Because it only had a single bond and a single bond. So that's 1, 2, 3, 4 electrons. Everybody wants how many? 8.
Okay, I see what you got.
Makes sense. All right, bond properties. This is really wordy for information that is common sense. Okay? So the first thing we're going to start with is bond order. Do not let bond order confuse you. All you do is look at the number of bonds between them. For instance, let's jump down here for a second. There's a single bond between this carbon and this oxygen, so therefore I know the bond order is 1. There's a double bond between this carbon and this oxygen, so therefore I know the bond order is 2. There's a triple bond between this carbon and this oxygen, so therefore I know the bond order is 3. So we're not going to stress over bond order. That's literally as simple as it is. Okay? Everybody see that? Yes? All right. Now, bond length. What do we notice happen between the bond length as we went from a single to a double to a triple bond? It decreased. Now remember we talked about this yesterday. Why would it decrease as I'm going from a single to a double to a triple? Because, go for it, Bella.
The nucleus pulls in the electrons closer to it.
There you go. I've increased the electron density between the two nuclei. So therefore I've decreased the repulsion between them, so they're going to move in closer. Okay. Now, if we look at the chart, okay, let's look at the single between carbon and nitrogen, then the double, then the triple. What do we notice also happens to the bond energy as I go from a single, double, triple? It increases. Okay? So when it comes to bond energy, the greater the number of electron pairs between the pairs of atoms, the shorter the bond, which means the atoms are held more tightly. So that means my bond energy is going to go what? Up. All right, bond energy and bond dissociation energy are the same thing, okay? Remember, bond energy is just the energy required to break a bond, okay? Bond dissociation energy just sounds a little bit more formal because dissociation means to what? Break apart. So bond dissociation energy is just the energy to break apart a molecule. And so we symbolize that with a capital D, okay? To break something apart, do I have to add energy in or is energy released? I have to add energy in. So that means my bond energy should be positive, which means it's going to be endothermic. That means the opposite also has to be true. When I make a new bond, energy is released, which means making a bond is what kind of process? Exothermic. And if you think about it, in pre-AP, I showed you this last year, whether you believe I did or not. Right. Remember those graphs we did? Okay. No matter, overall, this is what kind of reaction, just looking at it. Endothermic or exothermic? It's exothermic. How do I know this is exothermic? Because my reactant started a higher energy than my products, which means overall I did what? I released energy, right? So I'm negative. Or if I draw the graph like this, overall, this is what kind of reaction? Endothermic. How do I know it's endothermic? There you go. My reactants are lower than my products. Okay? It doesn't matter whether the reaction is exothermic or endothermic. Every single time you go through a chemical reaction, you go through an endothermic and an exothermic process. Okay? To get the bond of these reactants to break, what do I have to do? What's my energy doing here? It's going up, right? Because I have to put in that activation energy. Why do we have to have activation energy for every single reaction? Because you have to add energy to do what? To break the bonds. Okay? So here, everybody remember your energy of activation? Okay? That energy to activate the reaction is energy that's being added in to get these bonds to what? Break. Because before I can form new bonds, I've got to do what? Break the old ones, right? Yes? Okay? Then, whether it's exothermic and I get a large decrease in energy, or whether it's endothermic and I only get a short drop in energy, every time I make new bonds, my energy still does what? Goes down. Because making new bonds always causes energy to be released, correct?
So the more energy that's released when it's made, it's like it tells how strong the bond is?
Yes. Okay? So if I was asking you between 1 and 2, which of these is a stronger bond? First one, right? Because more energy was released when it was made. But do we see how every time it happens, I'm going to have an endothermic and an exothermic process? When bonds are broken, it's always endothermic. I've got to add in energy. When new bonds are made, it's always an exothermic process. I release energy. Okay? Depending on how much energy was released determines whether overall it's exothermic or overall it's endothermic. Do we see that? Yes? Okay. We got to get that. Last thing for today is right here. Okay. All right, calculating reaction energies from bond energies. Do not get this confused with the thermodynamics. Okay? In thermodynamics, we do the sum of the energy of the products minus the sum of the energy of the reactants. Okay? When we do bond energy, we do it backwards. We do the bonds broken, which is your reactants, minus the bonds made, which are your products, because we're just talking about the energy found in the bonds. Does that make sense? Okay. So we're not talking about the overall reaction, we're talking about the energy found in the bonds. So do not get that confused.
Miss Miller,
Yes, ma'am?
would you send Chelsea Porter to the office when she'll be back?
Yes, ma'am, hang on one second. Anybody know where Chelsea went?
I'll get her.
Okay, thank you. No, it's okay, Olivia's going to get her.
Could you just send her to the office?
Yes, ma'am.
Thank you.
I didn't mean literally hang on. All right. Delta H of the reaction is going to be reactants minus products. Okay? So the energy that it costs to break them apart minus the energy payoff. Okay? Again, don't get this confused with thermodynamics equation when they ask you for the delta H of the system. Okay? You're still doing products minus reactants on this. The only time you're going to do reactants minus products if they're asking you for bond energies. Everybody got that? Everybody with me? We're not confused? Okay, because Saturday when you go to your study session, it's going to be about thermodynamics. And so it's always going to be all about products minus reactants. Okay, do not let that confuse you with bond energies. So here is a chart of bond energies that is contained within a bunch of bonds. And then exercise 5 asks us, using the bond energies listed in 8.4, calculate delta H for the reaction of methane with chlorine and fluorine to give Freon 12 CF2Cl2. Okay? So again, because I see that they're asking me to use bond energies, I'm going to do what? Sum of the reactants minus sum of the products. So I'm going to say delta H, the reaction, is equal to sum of the reactants. This is CH4. So if I drew this, it would look like this, right? So what bond am I looking for? The bond between what? Carbon and hydrogen. So I go up to the table and I say, okay, so the energy, the bond energy in a CH bond is 413. Okay? How many CH bonds do I have here? 4. So I would do 4 times 413. Do we see that? Yes. Plus Cl2, that would just be a chlorine bonded to a chlorine, right? So that's only one bond, but how many of those molecules do I have? 2. So I'm going to have to multiply that by 2. And I find a chlorine, somebody help me out, there we go. 239. Plus F2, that would just be chlorine to fluorine. But since I have 2 of them, I have to multiply it by 2. So fluorine to fluorine is 154. And those are all of my reactants. We see it? Minus. Uh-oh. This one's going to get a little tricky. This is CF2Cl2. Who's going to be in the middle? Carbon. Okay. I'm going to have a fluorine, Cl, Cl. Hang on 2 seconds. So, how many carbon to fluorine bonds am I going to have? 2. So I'd do 2 times whatever it was for HF plus 2 times whatever it was for, for CF than it was for C to Cl. And then we would finish it out, and I'll see you tomorrow.
I feel like I missed